The main talk here is like moving from Python cluster to Rust. So we had a Kubernetes cluster. But this kind of talk is about all the different easy win methods you can do to transfer from Python to Rust. So I'll give you a quick whistle-stop tour. Because the thing is that people always say that Rust is really hard and there's a lot of moving parts. And that's not true. There's a lot of myths. So that's what we're going to try and cover. So a bit about myself. So I'm Maxwell Flitton. I'm a software engineer at Surreal DB. I wrote the book Rust and Web Programming. I also wrote the book Speed Up Your Python with Rust, which we'll cover some of the techniques here, how you fuse Python with Rust. And currently writing the O'Reilly book on async Rust with Caroline Wharton. And this is how you build your own custom async runtimes, your own queuing systems, and then how you actually execute them. If anyone's interested, we're implementing custom async runtimes in the key value store for Surreal DB. That's open source, so I can just point you to the code and you can have a look at it. So I always just put this in just because there's always someone saying, why Rust? I think everyone here kind of knows why we're going to switch over to Rust. And you kind of get that lovely safety, you get that performance and you get that memory safety. And it's kind of just, it's that sweet spot. But people say, well, it's memory safe, but Python's memory safe. And it's like, yeah, but is Python really that safe? So we'll have a look. This is the example I always use. So here we have this object, and then we put in a value, and then we put it in one dictionary, then we put it in another dictionary, and we change the value in one of the dictionaries, and then when we print it, you see that they're both pointing to the same object. They're both pointing to the same memory ID, and both have been updated. This isn't actually consistent, so you do it with objects, but if you do primitives, like integers or something, it won't do that, and it'll just point to different ones. So when I see ununit tested Python, I kind of freak out because it kind of has this graph-like memory structure, and it's really actually not safe. It kind of sweats under the hood, does all these weird things, you don't really know what's happening. So it's so I always say this when people say, well, Python's safe. So I say, well, it's not actually as safe as Rust. And if we try and do the same thing with Rust, you'll see that it'll say, look, you've moved it in here, you've tried to move it into there, what you're doing, you have to clone it, you have to put a pointed to it and guarantee the lifetime, that sort of thing. So hopefully, because it's only a 15-minute talk, I'm just going to assume that I've convinced everyone to adopt Rust. So it's like, well, how do we adopt Rust? And the first one is the PYO3, and this is essentially how we build Python modules in Rust. And this is a setup, so if anyone's written Python before and they've written their own modules, you'll understand this, right? You've got your setup here, and then it just kind of executes and it builds its own module. But you can see that we just import this lovely thing called setup tools Rust. That's literally it. And we define the PYO3 binding, and we point to where it is, and it will compile it into your module too. And in order to do that, PYO3 just has some lovely PyFunction macros. You can also build your own custom objects. You can inspect Python objects that come in. You can see that there's a PYNE, so it's kind of saying, I don't know what you're going to pass in here, but then you can like downcast it and you can unwrap it and see what's there, or handle it however you like. And you can see I'm doing some async here. I'm kind of blocking on there because Python's not really async, right? So whereas the Rust code was async, so I had to kind of block it. But you can see it's like it's super easy. And then what you've got here is you just import it, you define your own module, and then you just wrap it. And then, again, it's got all these lovely macros. So if you're in Python, you just say from Rust underscore Surreal DB, import, and you can import any of these and just run them in your Python code. So that's a really easy one. And if you want to dip your toe in, that's so easy to do. I highly recommend it. We can also use like advanced GitHub actions with matrices, and we've got some open source stuff because Surreal DB is an open source database, so we can just point you to anything there. And we build the binary wheels. So that means that the user doesn't actually have to have Rust installed. They can just pull the right wheel, and you can compile them all in your GitHub actions and then store them. So the next one is, let's say you don't want to build your own server yet, but you still want to use it a bit more than just importing it directly into Python. We can actually fuse Rust with Redis. So we can build our own custom Redis modules. And Redis actually supports this officially. So obviously it's not as good as Surreal DB, but I'd still recommend it. And this is how we do it. It's really not that hard. So on the left is our cargo, and we've got we call it session module, but we've got our Redis module. That's our dependency. That's the official Redis one. On our right is our Docker image and how we build it. And you can see here that we do our Rust, we compile our app, then we do a 2-layer, we add the Redis and we copy it over, and then we load it. And that means then you've got your Redis module running in Redis. And these things that are commented out are extra things you want to add if you actually want to put Python in there. So we kind of played around. I don't recommend it, but you can do it, where we actually got the GIL inside Redis, so you can actually run Python inside Redis through Rust, which is Redis is single-threaded, so it's not that great, but you can do it, right? And again, it's not that hard, right? So they've got lovely macros. You can just define your own commands that we pass in. You import your own logic. And this is a simple example. It's not all of it, because I don't want to have a whole thing. But, Redis strings, you can actually open writables, you can check certain things. So the reason what we did when we played around was that we had it where we had user sessions, and they had a certain time before they timed out, and they had a certain user role. So when you hit the Redis database, it did a few checks. So it checked to see if the user was actually there, checked what role it was, checked if the timeout has actually happened. If it hasn't, it updates the last interacted by, and then sends it back to the server. So you'd usually be doing 2 or 3 hits, with certain checks, but you can have it all just in one database call. So that's another really easy win if you want to try and adopt Rust. So you just use Redis, essentially. You can also use the queues and the threads and that they also offer. How do we actually do it? So there's a bit of story. So me and Caroline, in our spare time, on our side business, the German government came to us and said, we want to build medical simulation. And this is actually the system that we have. It's a real diagram. And we had to build medical simulation software the German government started using, and they all kind of logged in and started using it, and the Python server started falling over, and we started switching over to Rust, and we started supporting all of this in Rust, just 2 developers. And people said, well, Rust, you have to write a lot of code, right? It's harder than Python, and this is another myth that's nowhere near as fancy as people think it is. And we can start with a few of these. Like the first one is traits. We want to really aggressively do our traits. So if you can see that we do our own traits here for the reader and the writer. And for those who have a Python background, maybe just dipping your toe into Rust, this is kind of like surgical inheritance. So another really good way of thinking about this is, let's say that we have a function that says deal damage, and we have like an orc, an elf, a human warrior, and we can say, oh yeah, as a Python developer, we'll inherit from a player class. And they'll all come in and they can deal and receive damage. Then you say, well, hang on a sec, a building can receive damage, but a building's not a player, and it certainly can't give damage unless it's a particular type of building. And then it starts to fall apart, and that's where you get your inheritance messes. And this is why Rust trait systems are so good and so powerful, because they kind of force you to have this kind of isolated programming. So you actually end up getting more flexibility when you start adopting traits as opposed to object inheritance. And we can really see this here. So most of you most probably already do this, but we can just start annotating traits, with the insert and the insertable, debug, clone, identifiable, but we can also manually do them as well. So in this user one, we don't actually want to pass back the password, so we don't. So we implement the serialized trait and just omit the password. And when you start to think traits, what we found out is that we actually start writing less code than we did in Python, and I'll show you some of these things. So here is an Attic's web. And we've got here the incoming body, the JSON body. We've got the serialized and we've got deserialized, and that's automatically those traits implement that. We've got a trait that's like get config variable. We did that ourselves, and that means you could either load it via environment or via a file, a YAML file, and this is for unit testing. The JWT, we implemented the from request, so that's automatically middleware, and that automatically inherits where you get your config variable from. And then we did our custom error, and we also did the to requests. That means that the custom error automatically converts itself into a request, to a response, and it has its own status. And then you can see these question marks, so they automatically bubble up and return just instantly responses. So you can see here that you've got some middleware, you've got some automatic serialization, you've got some error handling that just automatically converts it back into a HTTP response with error codes. Do you see that much code there? I don't see it. Then let's say that we want to mount it to our server. So you see we can pass our env configs, and we'll just mount this, and we have our our app that we pass through, which is our server. And again, with the env configs, we can have different configs for testing because you could just load that function somewhere else and just test it. And then this is where we start to work on layering our things. So you can see here we've got our JSON web, we've got our incoming body, custom errors again, and this time we built our own established runtime traits. So you can say, look, I yield the trait. If I pass in a mock, it's going to pass back something. If I pass in the live one, it's actually going to run the actual code. But this layering pushes us through to the last part of the talk, and that is nanoservices. So this is something we've been kind of working on. And with our layered approach, we have another server, and we can just start loading our servers directly into our binary. So we start getting multiple servers into one binary. And we noticed that we've got some features here called memory. And what this actually means is that if the feature isn't memory, do a HTTP request to a server. If it is memory, then it actually just calls it directly in memory using the function. And then we combine our SQL migrations into our binary as well. So we have all our SQL migrations for all our servers combined in there. And we have a function that calls that and hits the certain database. And then we can combine all our servers and allocate how many workers we want and then just wait on them. So they all kind of run. And then they all call each other in memory. And they don't all have to wait on a certain socket. You can just have one there, but they can all call each other in memory. How big do you reckon this cluster that's compiled into one binary is, wrapped in Docker? How big? Does anybody want to guess? Nobody's feeling adventurous. Pardon? 5. Oh, come on. 5 meg. for a Docker image. For a Docker image. Docker image you're going to deploy into Kubernetes. 200 meg. That's kind of like reasonable. It's kind of in between. So this is it here, compressed. So it does go up to about 50, 60 megabytes, 23 megabytes for all those servers. Not 5 meg. You could ruin it for me. Not yet, not yet. And that's because we do a 2-layer build. And with this 2-layer build, we kind of compile everything. Then we mapped all the dependencies in the binary. Then we copied it into a distroless build. And anyone who hasn't done distroless, that means there's nothing there. There's literally, if you get into the Docker image, into the container, there's not even a shell. You can't do anything. There's not even shell access. And then we copy over all the individual libraries, just the ones that we use. And then that's how we get to roughly about 50, 60 megabytes image. So in total, we should all adopt Rust because it's easy to integrate, right? We've seen that with the Redis, we've seen that with the PY03. It's really fast, everyone knows that, right? It's safe, tiny memory footprint of our distroless, and it simplifies the DevOps, right? We don't have any init containers. All our SQL is just all compiled into one binary. All our servers are compiled into one binary, into the same binary. So it just simplifies it. And that is it. That's just us kind of developing. This is me and Caroline, and we had some friends who kind of built it. And there's lots of really exciting things doing. Caroline, as you see, there's recently signed a contract with NASA in the consulting. And for me, on my spare time, kind of working with King's College and looking at surgical robotics, because they're the London Centre of Bioengineering. And we're building a protocol in terms of how medical devices and surgical robotics, they kind of all talk to each other. And it's all going to be in Rust, which is quite exciting. So hopefully the next protocol for medical devices will be Rust-based. Hoping that maybe some other department's doing something that they haven't told us, they'll beat us to it. That's probably the reality. But let's pray. And that's it.